Okay. So you might notice I've changed clothes. I'm remaking this video, and I fell into the pitfalls of being a little bit overconfident. I kind of prepared what I wanted to say a month or so ago, and then when I went to do it, I kind of missed some things. So I've kind of added some details, and I've fixed a couple typos and things in my notes, so I will send those to you guys. All right, so I want to talk about Bell's theorem. So in the last video, I went through the EPR Incompleteness argument, where they argued that it had to be true. They felt that local realism was part of nature, and they showed that quantum mechanics was not compatible. That quantum mechanics didn't allow that, and so therefore there must be some other missing variables, or hidden variables they're often called, which would give a full theory of nature. And they weren't, Einstein, Podolsky, and Rosen were not saying that quantum mechanics gave the wrong answer. They were just saying that there are elements of nature, parts of the story that are just missed in quantum mechanics. The Copenhagen school of thought, on the other hand, felt like, no, quantum mechanics as it stands should be complete. And they use that. Even there are times where they needed that kind of for their part of their conceptual development, the way they developed thinking the ideas. They kind of, for it all to hang together, they needed it to be a complete theory. The other thing to say, though, is that even though the Copenhagen interpretation wanted to say that quantum mechanics was complete, and that in general there was no local realistic picture of things, it's true that when you look at some of the early papers, especially papers where Heisenberg and Bohr were using the Heisenberg uncertainty principle, and they really were talking about sort of a disturbance model for experiments, where the quantum mechanics involved a particle maybe moving around, electron moving around with some momentum, and then a photon coming in and hitting it and disturbing it. And the uncertainty principle came out of the disturbance. And even though none of the math behind doing full calculations relied upon that interpretation, that picture, when giving sort of intuitive explanations for why quantum mechanics work, they would use that language. And the EPR paradox kind of really forced them to stop and at least to stop and to be really clear and not make use of local realism. So up till the 60s, basically it was a matter of religion. You could go either way. There was no experimental way to determine whether Einstein was right and that there were hidden variables that somehow conspired to recreate the correlations in exactly the same detail that quantum mechanics predicted, or if quantum mechanics was right and there really is no kind of local realistic mechanical model of what's going on inside atomic systems. John Bell found a way to distinguish the two options. And if you think about it, Einstein et al. Never said what that theory of hidden variables would be. They just said there needed to be such a theory. Well, that's a nebulous thing, right? You're saying that there's some crazy theory, and it could be anything. It could be as complicated as you want. And so to disprove that idea, you can't make progress by just sort of ruling them out one after another, because there are an infinite number of things you might try. You'll never kind of exhaust that. But what Bell was able to do was just in one fell swoop make a clear distinction between predictions of theories which display local realism, so a particle has an actual momentum at all times and a position at all times, even if I can't measure it, versus something like quantum mechanics, which is non-local. And I'll go ahead and tell you, the upshot is, when you compare to experiment, that quantum mechanics is compatible with the experiments, and local realism is not. And so nature is non-local, fundamentally. And that's something we just have to kind of wrap our heads around, and even if we don't like it, we have to accept it and learn how to think about it. So the plan in these, I'm not going to go through Bell's original argument. It's a little bit, it's not that bad actually, it's pretty easy. What he does is he imagines that two people, Alice and Bob, let's say, receive entangled spin states, and they make measurements, and instead of just saying Alice and Bob measure, say, along the x-axis or the y-axis or the z-axis, he instead imagines that they could separately choose to measure properties along any axis, and then he studies the correlation, like what are the odds that person, and that Alice measures +1 along the 45-degree angle, and Bob measures +1 along the 60-degree angle. And what he shows is that there's a difference in the type of correlations you would expect for any theory displaying local realism, so that a particle has its attribute the entire time, versus a theory like quantum mechanics, where the attribute is really only determined upon measurement, and then before measurement there is no particular value of a certain attribute. So, that necessarily means that separate systems are non-locally entangled. So what he did was he considered arbitrary kind of measurements along arbitrary angles, and then looked at the sort of bounds on statistical distributions, and he found that they're what you could distinguish, kind of Einstein's view versus something non-local. I think it's, but really we're thinking quantum mechanics. What I'm going to do instead is, because I kind of like it, I'm going to follow notes from David Tong. David Tong's got great notes on all sorts of areas of physics, from quantum mechanics and classical mechanics all the way up to string theory and relativity and quantum field theory. I mean, he's a really great writer. Just a really clear thinker, and really clear when he presents things. The reason why I like it is because he's getting at the same point using things that we've seen through the course of this summer. And so we don't really have to introduce anything very new to this. And then I'm going to go through a different way to get at the same point. And it's using the so-called GHZ state. I'll explain what that is. It really goes back to a paper. What I want to go through goes back to a paper by David Merman, which I think kind of highlights the issue in the cleanest possible way. And it's a sort of, it kind of describes it. If you read his paper, which is much cleaner than what I will do, he writes it in a way that you could explain it to your grandmother or grandfather, and they could see why nature is weird. Okay, so let's go through David Tong's notes. These are much closer to Bell's original kind of strategy than the David Merman type argument that I'm going to give before. I don't know that's actually using it to test Bell's theorem or to reproduce Bell's theorem. I don't know that's not really his argument, but I don't think. But his little kind of classical picture of how things are, that's really what he did. It's nice. Okay. Anyways, David Tong's notes. So what we've seen, predicted by quantum mechanics, and what is actually experimentally observed, is that if you were to prepare a system in a spin state, and then say the z direction, and then measure the spin at some other angle, theta, in the xz plane, we get the following conditional probabilities. The probability of finding plus in the theta direction, given that we had plus in the z direction, equals cosine squared theta over 2. Remember, that's how that over 2, that was part of electrons being spin half. And similarly, the probability of finding minus theta, given that it was prepared in a plus z state, was sine squared theta over 2. Okay, so that's familiar stuff. If you don't remember, go back and consult the notes on spin, I don't know, probably 3, 4, 5 times or weeks ago. All right, now, just a reminder here, when I say plus or minus theta, what I mean is you're to find it in the state, so plus theta would be the state cosine theta over 2 plus z plus sine theta over 2 minus z, and minus theta is minus sine theta over 2 plus z plus cosine theta over 2 minus z. Okay, so the way I kind of try to remember it in my mind is plus and plus get the cosine, minus and minus get the cosine. Mixed ones have a sign. You have to remember where the negative sign goes. So right now we're just talking about one spin system. You know, you can use any basis, basically, plus or minus z or plus or minus theta. They're both equally good, and you can go back and forth using these relationships. All right. Very good. Now, Bell's theorem, or more generally, just entanglement, is an intertwining of properties between two separate spins, or two separate systems. Well, okay, so these are properties of just one system. So now we're going to move into our entangled state. I'm going to use the same notation I did in the EPR video. Or actually, I think I introduced it in the multi-particle states video. And we're going to use here the anti-correlated, so I put an A, state with a minus sign in the superposition. And I'm choosing this because it's a spin singlet, which means it doesn't change, the form of it can't change when you make a rotation. So I'd write that as, remember, I've got now two particles, two spin states, two spin half particles. One goes one direction, one goes the other. And we're going to imagine somehow we can prepare them so that particle 1, that'll be the label on the left, is in the plus state, say in the z direction. Particle 2 is anti-correlated with it. And then, because it's the minus state, I subtract in the superposition, and then I get minus z plus z. Okay? So that's the anti-correlated antisymmetric state. The antisymmetric is the minus in here. Now, because it is rotationally invariant, it's a spin singlet, which is the same as saying it transforms as it behaves like a scalar. Even though I've picked a basis correlated with, z, but I could have chosen a basis correlated with x or y or theta, so arbitrary angles, and the labeling, the state doesn't care. So that means if I just replace z with x or y or theta, nothing can change. So I could write this, for example, I'm using the fact that it's a rotationally invariant state. One way you can see this is that if you apply the total spin operator to this state, you get 0. And the total spin operator would be Pauli matrix. I'll remind you what these are in a minute if you don't remember. For particle 1 plus Pauli matrix for particle 2. That's the total spin operator. And if you apply this to this state, you'll get 0. So that's one way you can confirm that. All right. Great. Now, these are fine. Particle 1, particle 2, particle 1, particle 2. Or you can write it, so you can write it with z's and z's, or thetas and thetas. Or what we will want to do for our little cute proof is to do something which looks totally stupid. We're going to write the same state, but I'm going to write particle 1 in the z basis and particle 2 in the theta basis. Again, these are just choices of basis. That's not physical. You can do that. And there's nothing that says that you have to write them both. They're separate particles. Their observers could use different basis descriptions. So I'm using the relationship between plus theta and plus z and minus z, and minus theta and plus z and minus z that I just had on the previous board. And what I can do is regroup things, and if I've done all this right, I can have yet a third way to express this state. All I'm doing is just using the vectors that I had before. So if you have the advantage of stopping and rewinding and look at the vectors that I wrote down, or look in the notes, you can see where they come from. So we have 1 over root 2, that's from here, times, well, when I turn this plus theta into something in terms of z, I get sines and cosines. And the same way with the minus theta. So pulling out things which are like cosine of theta over 2, and then I get plus z minus theta. I think I've got all these signs right. Minus z plus theta. Okay, that's this one. No, it's actually a mix. It's not even that simple. I've rearranged things a little bit. So you just, if you want to do this, you have to just sit down, pause the video, and just work out how to go from the theta basis to the z basis on the first factor, not the second factor. Okay, and then I have plus, and I'm going to get a sine theta over 2 times, And now I'm going to get plus z plus theta plus minus z minus theta. Good God, what a mess. Looks terrible. It is terrible. But really, when we compute probabilities, we're going to pick off the coefficients. It's just going to be things like the square of this number, this coefficient, or the square of this coefficient. So the actual probabilities aren't so bad. All right, so I'll give you a second. You can kind of write that down. Pause the video. There you go. All right, so using this state, I have to erase it now, but I'm going to write down the probabilities that these states would predict. I wouldn't have you do all this if the payoff wasn't so important. Okay, so what you would find, using those states, take the dot products, calculate the probability. Remember, the probability is you compute the probability amplitude, the bra times the ket, take the magnitude squared. So you would use those and you'd find the probability of finding plus in the z direction for, oh, I'm sorry, I jumped the gun, 1 second. So what we're going to do is the following. We have these particles, particle 1 and particle 2. Both spin half particles going off. Over here is Alice. And over here is Bob. I don't know why we choose Alice and Bob. There's probably some reason. But it's common to talk about the measurers, the observers, the experimenters, and talk about them in terms of Alice and Bob. Okay, so what we could do now is calculate the probability that Alice measures plus the probability that Alice measures plus z, so that's A, and that Bob, so Alice is going to make measurements along the z-axis, I should have said that. Bob is going to make measurements along the theta direction. Okay, so how would you calculate that, since I've kind of bumbled that? What you would do is find the probability amplitude, go plus z for Alice, that's spin particle 1, plus theta for Bob, that's particle 2, with the state A minus that we just had, that's probability amplitude, and you would take the magnitude squared. And what you'll see, if you go through all this, Alice is particle 1, Bob measures particle 2. What you'd see is that this picks off one of those 4 terms, and then you take the magnitude squared of it. And this gives you 1/2, that comes from the square root of 2, and we get sine squared theta over 2. Okay? So I'm not expecting you to just do it right here. What I'm expecting you to do is to pause it and check with the previous screen, the previous state that I wrote down, and it will fall out. Similarly, we have the following probabilities. The probability, I better look at my notes so I don't screw it up again. This is where I went wrong with my first video. Well, one of the places, I had a couple of mistakes. It's not a good day. Minus, in the theta direction, according to Bob, that is going to be 1/2 cosine squared theta over 2. The probability of minus z, according to Alice, and plus theta, according to Bob, is also going to be 1/2 cosine squared theta over 2. And finally, the probability of minus z, according to Alice, and minus in the theta direction, according to Bob, is 1/2 cosine squared, sine squared theta over 2. So if you pause the video, you should go back if you want to work these out and understand it really, and see that it's not that hard, go back to the previous state that I had for where I wrote Alice, or particle 1, in the z, along the z-axis, and particle 2 I left in the theta direction. Use that version of this state. And just take the inner products with the corresponding ket vectors, and you'll just pick off these coefficients. And you only have to take the square of them. All right. Whew. Okay, so this is what quantum mechanics would predict, right? Because where do we get these? Well, we had bras and kets and did quantum mechanics, and that's what we would get. And these match experiment. Okay. So now, so that's what quantum mechanics is. What we want to do to kind of understand Bell's point is to now switch gears and not talk about quantum mechanics anymore. Instead, let's think about some unspecified, local, real, when I say real, I guess I'm saying, meaning some theory where objects or degrees of freedom move around dynamically and interact, and they carry their properties with them, like in a suitcase. As they walk around, you know, they carry their position and velocity and spin and everything with them as they walk around. And we don't know anything about the dynamics or interactions or anything like that. What we will assume is, like Einstein, that, you know, relativity is good, that, basically, you know, all the same assumptions that Einstein made. All right, now, okay, I should have said this. If Einstein is right, then these probabilities should be interpreted as probabilities of ignorance, and if Einstein's wrong, if the Copenhagen school of thought is right, then the probabilities in quantum mechanics are new, kind of irreducible elements to the theory, or in the theory. I should have said that at the beginning. But that's really what we're trying to decide. That's one way to, no, stop. Okay, so now let's think about hidden variables. We still have Alice and Bob. Okay, we still have Alice and Bob. We're going to just assume that there are some hidden variables, and that you know, the degrees of freedom we talk about, or the things that we measure, are the values of some sort of random, or some sort of variable. Just call it S, following David Tong's notes. And S, you know, you could have S in the Z direction, say. And it could be plus or minus 1 to match experiment. It has to be true. And you could imagine that there's some S in the theta direction, which is plus or minus 1, again, to match experiment. Or any other direction, you have the same thing. We don't know the rules that such little bits of information must follow, but Einstein would say, well, but there has to be some sort of label which just has specific values all the time as the particles move around. So what we can do, and what we will do, is assume that these variables exist in such a way that they can reproduce the previous probabilities that I just had on the board, and I'll rewrite them there. But now those should be interpreted as probabilities for hidden variables, or probabilities of ignorance. Okay, so we're going to assume that, you know, the rules for these hidden variables are that the probability, I'm going to write HV for hidden variable, so that you distinguish it from the probabilities in quantum mechanics, you know, a priori. Even though they evaluate to the same thing, logically, they're different. You know, they have a different origin. Okay, and I'm going to write S. Boy, I really labeled everything. The spin along the Z direction, according to Alice, is plus, and the spin in the theta direction, according to Bob, is plus, but that's got to correspond to the plus plus case that we had before, so that is going to be the same. 1/2 sine squared theta over 2. I don't want to write all these out. I guess I will. Okay. The probability, again, I'm thinking of this as now as a hidden variable. I mean, it's whatever these hidden variables have, we're going to, for them to have a chance, they have to reproduce these results. So we're going to just assume that they have these. S, Z, Alice equals minus spin theta Bob equals plus. That's going to be 1/2 cosine squared theta over 2. Anyway, you just keep going now. If Alice measures plus along the z direction and Bob measures minus along the z direction, you also get 1/2 cosine squared theta over 2. And finally, if Alice measures minus along the z direction and Bob measures minus along the theta direction, that'll happen with the probability 1/2 sine squared theta over 2. So really, it's the same combinations of plus and plus gives 1/2 sine squared, plus minus gives 1/2 cosine squared, plus minus, I just said, minus plus, plus minus, they all give 1/2 cosine squared. And minus minus give 1/2 sine squared. Okay, so, right. So it's the same pattern. It's really, we're saying that if there is a hidden variable theory able to reproduce the things we see, it better have this property. Even if we don't know the rules underlying and the kind of the cause of it, we don't know how to do the statistical mechanics to kind of account for this, but evidently it would have to have this property to have any chance. Okay, now, all right. The next is a little bit of a trick. Maybe not a trick, but the thing is, the other thing we do know is that in these experiments, the spins are anti-correlated, and that's experimentally true. So that needs to be true. It is manifestly true in the quantum mechanical state vector, but for hidden variable theory, they have to. That's a measurable property. This hidden variable theory has to have that, which means that the probability. Basically, what it means is that the spin in a certain direction of Bob is always going to be minus what Alice would measure if she measured in that same direction. So what I'm really saying is the spin in the direction Bob is minus the spin in a certain direction as measured by Alice. So that's why is that different than quantum mechanics? Well, in quantum mechanics, you wouldn't say, the Copenhagen interpretation of quantum mechanics would be that you wouldn't say that the spin is anything until it's been measured. You're just saying the outcome of an experiment is something, but the actual spin is not any particular value until it's been measured. But in a local realistic theory, like Einstein would want us to consider, he would want to say that the spin is always something, and furthermore, because they're anti-correlated, you would be able to say that whatever the spin of Bob is, in kind of a classical sense, then the spin of Alice is simultaneously minus that value. Okay? So because of that, we can reinterpret these same distributions, and we can say that instead, even though Alice only gets to measure one spin in one direction at a time, Einstein would say you could, the spin along any other direction has a value, it's just not known. So he would say, we could come up with then, we could reinterpret this as saying a probability that the spin Alice measures in the z direction is the probability that is +1, and then you could reinterpret this. Okay, so if this is the spin Bob measures in the theta direction, then that is minus what Alice would measure in the same direction. So you can change that to a minus. So, and similarly, you can. So these were Bob. This was Alice. Now I wish I had written it all down. This is Z Alice, Z Alice. This was theta Bob, theta Bob. Now I can reinterpret this in terms of the value of Alice's hidden variable in the theta direction, which is minus that. And then same way here, it's a plus Alice, and now a plus Alice. Okay, so what happens is basically you're just shifting, you just flip everything by a minus sign. Now I'm talking about two spins that Alice could possibly measure. So if Alice, this would be Alice's particle in this theory of hidden variables. This hidden variables theory, Alice has this particle, has this spin degree of freedom, and it has different values depending upon, at all times, depending upon which direction she measures. And evidently, for this to hang together, it must be that the probability that the spin value is plus for her in the z direction and minus in the theta direction is given by half sine squared. And the probability that it's minus in the z direction for her and simultaneously theta in the minus in the theta direction is half cosine squared theta over 2. All right? This contradicts what quantum mechanics would say, because, well, first of all, there's a problem with saying that the spin is of the system is anything until it's been measured. Okay, but furthermore, there's no way in quantum mechanics that you can assign simultaneous values to spin in different directions. That just could never make any sense in quantum mechanics. Okay, but if it's a hidden variables theory, then you can. Then every variable has a value at all times. That's kind of the point. And so therefore, you should have a value for each of these at the same time. And evidently, for this to work, you'd have to have these probabilities. Okay, it's all weird, I know. Again, the result is important, and so that's why I'm pushing through. Okay, great. Now, these hidden variables probabilities are ignorance interpretable. So these should obey the usual kinds of statistical laws. So in particular, if you have any property, say in a hidden variable, A, so the probability of any property A in this hidden variables theory should be the sum over conditions, just call them B, of the conditional probabilities. And you can put these in any order. In my notes are like this. Okay? This is the composition rule we had when I was talking about, classical amplified macroscopic probabilities. It's just the usual probability, the way that you can go from conditional probabilities to total probabilities. Okay, so the total probability of getting A is the sum of the probability of getting A given every possible value of B. Okay? So we should have the same thing for our spin systems. So if Alice can have, so if we can talk about the probability of Alice's particle simultaneously having a value spin in the z direction and spin in the theta direction, well, we could also think about a third angle direction, call it phi. Okay? So once you can do, if you can do, because we can do any measurements in any direction, and each one always has a value according to Einstein, and so you could consider higher and higher conditional probabilities. All right. So these are just higher conditional probabilities. I don't want to write that. Oh, these are again hidden variable. So once you can do 2, you can do 3, 4. You can do any angle. In fact, you could do all of them. And you could integrate over things, all the angles, things like that. All right. What we do is the following. Consider the conditional probability for Alice's particle to be found in, sorry, to have values. I don't want to say to be found in, I want to say to have values because it's a hidden variable theory. S in the theta direction, simultaneously having a value phi, S in the phi direction. Some value, they don't even have to be the same, but some, right? Okay. Well, I could use my composition rule for conditional probabilities, not on these, basically to relate this to a sum of triple conditional probabilities, I guess. I don't know what to call them. All right, so I could write this as the sum over plus or minus z these are spins. Well, let's call it S. Spin. I'll just call it S for spin along the z direction measured by Alice. That looks terrible. But remember, if you sum over a conditional value, sum over all possible values, it just goes away. Right? Now that's what we have for classical probabilities. So so then we can actually, let's just write this out and be a little bit more explicit and just sum over values where this is plus or minus 1. And I can write this as the probability in variable plus z Alice, s theta Alice, s phi Alice, plus probability minus z Alice, s theta Alice, s phi Alice. Okay, I'm just writing out the sum. And then, and here's the clever bit. And this also I messed up because I didn't read my notes carefully enough before starting in last time. I should have reviewed a little bit more. This is true, but I can also make a true statement. If I add a positive number to one side and don't touch the other one, it becomes an inequality. And so I'm going to add two positive numbers, and the trick is to choose just the right positive numbers. And what I'm going to do is add plus p, hidden variable, plus z Alice, comma, s theta a, comma, and then watch what I do here, minus s phi a. So I'm adding a term with, basically, if I had some value of spin for phi in the phi direction, I'm choosing the opposite value over here. And I don't know what this is, but I know it's a probability, so it's bigger than 1. Or sorry, it's bigger than 0 and less than 1. I think I said bigger than 1 before. It should be bigger than 0 and less than 1. And similarly, I'm going to do something similar, but I'm going to add in the opposite on the theta direction and write p minus z a, comma, minus s theta a, and then s phi a. This is, Emily, if you're watching, this is where I fouled up in class, or when you were here. I put this minus sign here. So that was just a silly mistake. It wasn't wrong, it just was silly. Okay, so I had a true statement, and then I added something positive to one side. I didn't add anything to the other side, so now I have that is less than or equal to. I mean, I suppose these could be 0, so you could have side equality, but it's generally going to be less than. All right. Why? Why would we do this? Well, the thing is, now look at what happens. The spin of this hidden variable spin only has two values, plus or minus 1. Well, here's one value, here's the other value. Now, I don't know which is which, but it doesn't matter because we've got them both covered, summed over, and when you sum over conditional probabilities, they just go away. And here, so what's going to happen is these phi hidden variables, or the phi dependent hidden variables are going to go away here, and on this side, the theta dependent hidden variables are going to go away, and what we get is the following: that this probability is less than or equal to okay, so summing them like this eliminates one of the hidden variables from the probability distribution. Hidden variable. And so this one, the theta dependent one goes away, and here the phi dependent one goes away. And this is what we started with. Well, what's the big deal? Well, we're almost there. But we have explicit formulas for these, right? We have these probabilities. They're written, they're like half of sine squared and half of cosine squared, things like that. The last little bit is relativity. We don't know what this is. What we have are z's, correlations between, or probabilities between spins in z and theta. Here, we just have this. So there's a little bit, so we're going to use the relativity principle to say that, well, okay, whatever this is, it can't depend upon the absolute angle, because there's no absolute reference frame. So whatever this is, it can only depend upon the difference in angles. And if the angles are 0, you get, it would point along the z direction. So this is the same as, using relativity, probability hidden variable spin along the z direction, that'd be 0, comma, the difference in the angles. S, how am I going to write that? Theta, or guess it should be phi minus theta, strictly speaking. Okay, all right, looks terrible, I'm sorry. But basically, you're able to rewrite this in terms of, basically you're able to shift things so that if it's only a function of the difference in angles, you could kind of rewrite it so that the first argument has 0 as an angle, and then the difference in angles appears in the second argument. Okay, just think about that. All right, and why is that useful? Well, we have a formula for this. So let me choose a particular case. Okay, so might want to pause this and write this down. All right. I'm going to choose specific cases, pluses and minuses, and you'll see. So what I'm going to do is choose S theta A equals plus and S phi A equals minus. And then I can write that previous thing as probability, hidden variables, plus Z minus theta, or phi minus Z direction. Is less than or equal to probability hidden variables plus Z theta, plus theta plus probability hidden variables plus, minus Z minus theta. Okay, that's what we had. Take that previous line and evaluate it for the special case where these spins have these values, or using the formulas in terms of angles, what we get is it would have to be that for any angles, theta and phi, that sine squared theta, theta minus phi over 2 squared is less than or equal to cosine squared theta over 2 plus cosine squared phi over 2. I just fear that I fouled this up again. You got the right ones. I think I want cosine here. I don't think I'm going to be able to reconstruct it on the fly. Give me a second. I think I want cosine there. Plus, minus. I have sine squared. I think, maybe I'm okay. So this is supposed to work for any angle. In David Tong's notes, he says choose theta equals phi equals 3 pi over 4. And you know what? I didn't actually type it in. I think think what he might want is minus theta equals phi. I think that's what he wants. The problem, I don't have a calculator here. If you choose them to be equal, the left-hand side's 0 and the right-hand side's never negative, so there's no problem as far as I can see. But if you choose them to be opposite, then they add up. I think that's what you want. Anyway, so the point is this. If there's a hidden variable theory that can reproduce quantum mechanics, when you work out the implication of them having a value and work out the probabilities, you can get an inequality, and that inequality is not true. It's not satisfied. So what it would mean is that evidently there is no hidden variable theory that can give you these probabilities for all angles. And we measure these probabilities in experiment. And so, so that would mean that there can be no hidden variable theory which describes or reproduces quantum mechanics. So Einstein was wrong. It simply is not true that you can describe nature by a bunch of little marbles that carry around a position of velocity, and they always have some position and some velocity at all times, regardless of whether we look at them. Evidently, there's an inherent non-locality to nature. So this doesn't rule out non-local theories. You could have a non-local theory where particles always have a position and velocity, but they have interactions where they sort of send signals across the universe instantaneously, non-locally, and that would have, you can get around this with that kind of a theory. Or something like quantum mechanics, where it is non-local, and there you don't even say that the particles have properties when they're not, if they're not being measured. So that's Bell's theorem, kind of in the spirit he derived it. His bound was a little different, but it has the same. This one has the flavor of his theorem, the way he approached it. All right. So evidently, nature is fundamentally non-local. All right. I'm going to now describe the an equivalent result following the thought, the line of reasoning that David Merman used. I think I'm running low on battery. So what I'm actually going to do is pause this, or stop this video, and then I'll upload a video on this last version of Bell's theorem, which I think is the slickest, most intuitive, cleanest way to write it.